slide di oggi. Vi chiedo magari a qualcuno di voi di registrarla pure, è sempre meglio avere una copia in più della lezione, ok? Per registrarla dovete andare nell'angolino in basso a destra, c'è un menu, e la prima cosa che leggete è registrare la lezione, che dovrebbe poi salvarsi nel vostro desktop, credo. Nel vostro, scusate, Google Drive. Allora, possiamo iniziare. Quindi vedete la slide a schermo pieno adesso?
Sì, vediamo la slide a schermo pieno.
Ok, allora
in realtà non è possibile registrarla contemporaneamente.
No, infatti, perché sta registrando lei.
Ah, va bene. D'accordo, va bene. Allora, facciamo una cosa, io esco anche da qui, così facciamo la banda. Torniamo qui. Allora, possiamo iniziare con la lezione. So now, as we switch in English. So last time we started discussing about the quantum electrodynamics, which is the quantum field theory of the electromagnetic interaction, which is the first one of the three that we will discuss in our course. And we derived, first of all, the Lagrangian density of QED that you see here also on the slide. So here, essentially, we find three main terms. The first terms includes the kinetic term plus the mass term of the fermion, for instance, an electron. Then we have an interaction term where the fermion, which is described by this spin or psi, interact with the gauge field mu, which is a vector boson. And then we have also, in addition, a kinetic term for the gauge boson. Okay. What we don't have here is a mass term for the gauge boson. Okay, this is fine because we know that the photon, which is the gauge boson of the electromagnetic interaction, is a massless particle. Okay, but if this would not be the case, and we would want to add a mass term by hand, okay, for the gauge boson, then we would immediately break the gauge invariance of the Lagrangian density. So the Lagrangian density would not be any more invariant under local U1 transformation. Okay, so we don't have this mass term, and we are happy because photons are massless. Okay, we will see that this is actually a big problem for the weak interactions, where the gauge bosons, the W's and the Z, are massive, actually very massive, and this will be solved by through the Higgs mechanism, as we will study at the end of the course. Now, how did we derive this Lagrangian density? So this is the procedure or the recipe. So if you remember, we started from the Lagrangian density of a free Dirac fermion. Then we required the invariance for local U1 phase transformations, where the parameter of the transformation depends explicitly on the space-time coordinate, so it varies in each point of space-time. In order to make the Lagrangian density invariant under this transformation, we need to substitute the standard derivative with the covariant derivative, okay, which are given by the standard derivative plus an additional term here, which includes a new object, okay, which is in fact the gauge field, okay. And the gauge field has to transform properly under this U1 local transformation in order to preserve the gauge invariance of the Lagrangian density. So we need this additional term here with the derivative of the alpha term, which will cancel the one coming from the derivative, coming from the mu term, okay, in the transform of the mu term. And finally, we add the kinetic term for the gauge field, which is given in terms of the electromagnetic strength tensor, F mu nu, which in turn is given in terms of the gauge field in this way. So the mu nu minus the nu mu. Now, this is the, let's say, the basis of the quantum field theory approach to quantum field theory, to quantum electrodynamics. Today, we will now switch to the complementary approach that was historically the first one that has been developed, that is based on perturbative techniques. Okay, so we call this the Feynman approach because Feynman was, together with two other colleagues, the first, indeed, person to introduce the perturbative approach to the quantum electrodynamics. And specifically, he developed the rules for evaluating the transition matrix elements, okay, so the transition probabilities, so at the end of the cross sections, for the various electromagnetic processes, and for representing them graphically through special diagrams, which are the famous Feynman diagrams that you know already. We will study a lot this in detail today. Now, Feynman diagrams are not only useful pictorial representations of the various processes, but instead they represent a specific mathematical expression in the sense that each diagram corresponds to a specific term of a perturbative expansion of the scattering amplitude, as we will see mainly tomorrow. And each symbol of the diagrams corresponds to a specific term in the transition matrix element, as we will see today. And this correspondence, okay, between Feynman diagrams and matrix elements, so transition probabilities, is encoded in the so-called Feynman rules for QED. Okay, and similar rules have been developed also for later on for the strong interaction and the weak interaction, as we will see later on.
Professore, scusi se la interrompo. C'è uno studente che chiede di partecipare.
Ah, io non posso
Andrea Di Donna.
qua, deve farlo Gambetti. Vediamo se... un attimino. Allora.
Entrate allora.
Gambetti si è sconnesso?
No, sono ancora qua Luciano, però io non vedo la sua richiesta. Tutti quelli che ho visto li ho fatti entrare, però questo Andrea Di Donna ancora non lo vedo. Provate a dirgli di provare a riloggarsi.
Io l'ho scritto.
Ok.
Ok, intanto grazie Michele. So let's continue from this point. Okay, so let's consider for the moment a generic electromagnetic process, A plus B that goes into C plus D. Okay, we can represent it diagrammatically in this way, and then we will learn how to construct Feynman diagrams. So the convention is that always the time runs from left to right. Okay, so A and B are the two initial states. Then we have some interaction here, electromagnetic interaction, which is mediated by indeed the photon, which is the gauge field of QED. And then C and D are the final state particles. Okay, so this is a generic first order level QED diagram. So how can we convert these into a transition matrix? So the matrix element for this generic process consists of three parts. So the first part and the third part are the strength of the interaction at the two vertices. So we have two vertices here and there. Okay, the vertices where the current flows like this, A to C, and the vertices where the current flows like this. For the moment, don't take care of the direction. So the strength of these interaction are given by these matrix elements. So psi C, V, psi A in general, and psi for the upper vertex, and psi D, V, psi B for the lower vertex. And in between, we have the bosonic propagator. Okay, so the propagator of the exchanged virtual particle, which is in fact a photon in this simple case. Now, how can we construct now real Feynman diagrams? Okay, first of all, we need to define the basic QED vertices. Okay, and then we will use these to make real processes. So what you see here, you have 6 different vertices here, okay, which concerning electron and positron are the only possible elementary vertices. So we have here the emission of a photon by an electron, the absorption of a photon by an electron, the emission of a photon by a positron, which is the antiparticle of the electron, as you know, the absorption of a photon by a positron. C'è qualcuno che ha il microfono acceso, per favore, potete mutarlo. And then we have the electron-positron annihilation into a photon, or the photon, the electron-positron pair creation from a photon. Okay. Now, take note, actually remember what we have already studied, that these processes here cannot be real processes because energy is not conserved. If you remember, we showed these, okay, using the relativistic relation between energy and momentum. Okay. So these cannot be real processes. Real processes you can only obtain by combining, okay, these objects here into the real Feynman diagrams. And you see some examples here. Okay, so when you combine properly these vertices, you end up with these real processes. So the first one is electron-electron scattering through the exchange of a virtual photon. That is also called the molar scattering. Then we have electron-positron scattering, which is essentially the same. Now we have a positron and electron. This is called the Baba scattering. Then we have two a little more complicated processes. The first one is Bremsstrahlung, that is the emission of a real photon by an electron. And in order to have a full momentum conservation fulfilled, this process has to occur in the proximity of the electric field of some nucleus, for instance, that absorbs the missing momentum. And similarly for the pair production, so a photon that generates an electron-positron pair, but also in order to have for momentum conservation fulfilled, this process has to occur in the proximity of some charged particle, okay, that absorbs this additional photon, which ensures absorbs the missing momentum, so which assures for momentum conservation in the process. Now, let's now go back to the formalism and how to derive the matrix element for generic, for the moment, QED process, and then we will study in detail the molar scattering and the electron-positron annihilation. So, if you remember, in one of the first lessons, we derived the non-relativistic transition amplitude at first order and inborn approximation. So, assuming that the wave functions were plane waves. Okay, initial state and final state wave function were approximated by plane waves. So this is, if you remember now, the expression of the non-relativistic transition amplitude in terms of the initial and final state wave functions. V is the potential energy that we split into a potential times a coupling constant, P0. And we derive these for the case of the Yukawa potential, if you remember, okay? And we end up with this general expression where we have here, in a sense, a constant in the numerator, which takes into account the strength of the potential and of the interacting particle, the fermion. And in the denominator, we have the q squared plus m squared. So if you just take these, 1 over q squared plus m squared, these, if you remember, we call the bosonic propagator. That essentially provides the probability amplitude for the exchanged boson, okay, to be emitted at one vertex and absorbed at the other vertex. And these, in this process, the momentum transfer from the two interacting particles occurs. Okay. Now let me also remind you that the Q here is the transferred 3 momentum. So it's given by the difference between the initial state and final state 3 momentum. Now, this was in the non-relativistic approach. Now, of course, we want to move to a relativistic approach. So the relativistic transition amplitude at first order is, if you see, is very similar, but there's also some important differences. Okay, first of all, you have a minus I on top of this. Then we are now integrating in the full phase space. So this is the 4-dimensional space. It's not just the 3-dimensional volume. And your wave function are now substituted by the Dirac spinors, okay, that you can see here in their generic plane wave expression. Now, one can do exactly the same, okay, similar, let's say, derivation that we did for the non-relativistic case. And when you do this in the relativistic case, you end up with this expression for the bosonic propagator, okay, which is a covariant expression because it is, of course, derived in the framework of quantum relativistic theory. So this is the propagator. In general, this accounts for a boson with mass m. Okay, for the photon, of course, this mass is 0, so we will drop this term here. So Q square is now the 4 momentum transfer, which is encoded, if you remember, by the T Mandelstam variable. So suppose you have an interaction like this. So the initial state particle with 4 momenta P1 and P2, and final state particle with 4 momenta P3 and P4. Then the squared, the full momentum transfer is squared, is P1 minus P3 squared, or equivalently P2 minus P4 squared. Okay. And this is this term here. Then what about the numerator? This is the most interesting part, of course. The numerator denotes the sum over all possible spin states of the exchanged boson. So let's now see what happened specifically for the photon, which is the gauge boson for the electromagnetic interactions. And let's speak about the photon wave function first of all. Okay, so let's consider a free photon. A free photon field that we call a nu. Okay, free means in absence of charges or currents, just a free photon in space. So its wave function can be written in terms of a plane wave because it is not interacting, it is free, times an additional 4 vector that describe the polarization state of the photon. So this is the full wave function for a free photon. Okay, you have the plane wave here and the polarization, the 4 vector there. Now, for real photons, only 2 independent polarization states are possible. So suppose that the real photon propagates along the z direction, then the 2 polarization states are along the 2 transverse directions. So the first one is epsilon1 or epsilon x, defined in this way, and the second is epsilon2 or epsilon y, defined in this other way. So these are the two polarization vectors for the two polarization state of a free real photon. Okay. Now you can combine these two, okay, properly. So if you take this combination or that combination with a minus sign or a plus sign, you obtain the, let's say, left-handed and right-handed circular polarization of the vectors, okay, which corresponds to plus or minus helicity. So this is the way you essentially obtain right and left polarization of the photon, okay, as a combination of the two transverse components. What about virtual photons? Because now we are, of course, interested in virtual photons because this is what we actually exchange in interaction between two real fermions. Okay. So for virtual photons, the difference is a little bit different. There are actually 4 polarization states, 2 transverse, as for the real photon, but also 1 longitudinal and 1 scalar. Scalar means a spin equals 0. So we have 4 spin state, 4 possible spin state for a virtual photon. Okay. Now, it can be shown, we will not prove this, but just trust this. It can be shown that the sum over all possible polarization state of the photon, okay, at one vertex, at one upper vertex and the lower vertex, so when you perform this sum, this is exactly equal to the metric tensor, G mu nu, with a minus sign on top. This is the metric tensor of relativity. Okay. So now we can write the photopropagator in a compact way. Okay, we can just substitute this summation over the possible spin state of the photon at the two vertices, just with the metric tensor G mu nu. And so the photopropagator is just minus I G mu nu over Q squared. Of course, we also dropped the mass term because the photon is massless. Now, so let's now start discussing in detail the most simple electromagnetic process, that is the molar scattering. So electron-electron that goes into electron-electron. And let's do this twice. The first time now from first principles, and then we will derive the same matrix element in a much simpler way by making use of the Feynman rules, so the Feynman diagrams. Okay. So let's first start on first principles. So also to this will allow us to learn even more the physics that is beyond. So we start from the Dirac equation for a free electron of 4 momentum p. So this is the covariant Dirac equation. This is the standard solution, where U is, as usual, a 4-component spinor. Now, suppose now that the electron is not anymore a free electron, but it is embedded into an electromagnetic field. So we have to modify the Dirac equation and adding here an interaction term between the electron and the electromagnetic field. And the electromagnetic field can be described by these 4 potential, where phi is the scalar potential and A is the vector potential. Okay, is a 4 vector, of course. So your the Dirac equation for an electron into an electromagnetic field mu is given here. Okay, we just have an additional term, which is indeed the interaction term. Now, let me make a comment here. So you can obtain this interacting Dirac equation from the free Dirac equation by simply substituting the mu with the mu plus I Q mu, where Q is the electron charge, which for the electron is minus E. Okay, so if you make this change here, you would obtain exactly this interacting equation. But, as you now remember, this is exactly the substitution we made in order to make the QED Lagrangian density gauge invariant. Okay, so this corresponds to changing the standard derivative with the covariant derivative. It's exactly the same. Okay, and this connection demonstrates the complementarity of the two approaches: the perturbative approach that we are discussing now, and the quantum field theory approach that we discussed last time. Okay. Now let's go back to this Dirac equation, interacting Dirac equation. Now this Dirac equation can be also derived, okay, formally from this Hamiltonian, where we have a free term, okay, which accounts for the kinetic and the mass term. And then we have also this potential energy term, which now accounts for the interaction of the electron with the electromagnetic field. Now, the correct expression of this potential energy term into the Hamiltonian is given here. So Q is the electric charge, then we have gamma 0, gamma mu, and then mu is the electromagnetic field, or if you like, okay, now the two things are complementary. You can now interpret this as the photon wave function. In fact, here we can just substitute the photon wave function, which is the plane wave times the polarization 4 vector. So this is the expression, okay, of the potential energy that you have to put into the Miltonian in order to obtain this interacting Dirac equation. Now, what we want to calculate now is the matrix element for the molar scattering. So electron-electron into electron-electron. And so we will at the end put this into the general formula of the cross-section. So at the end we will really have a calculation of the cross-section for this elementary quantum QED process. Okay. And this matrix element can be obtained from first principle by describing the interaction at the upper and the lower electron-photon-electron or electron-photon-electron vertices, okay, in terms of the potential energy that I just gave you in the previous slide. Okay. So let's now go to the blackboard or the whiteboard. Ok. È riuscito a connettersi l'altro studente?
Sì, grazie.
Sì,
Ok,
sì, era
vedo qua delle mail, va bene. Ok, benissimo. Allora, ci spostiamo adesso sulla lavagna. Allora, ho preparato adesso questa pagina qui. Oddio, si è sconnessa, quindi datemi qualche secondo per riconnettere. Vediamo un po' se parte. Ok, allora dovreste vedere voi un foglio bianco, giusto?
Sì, vediamo un foglio bianco.
Giusto, sì.
Sì.
Ok, allora d'ora in poi questa sarà la nostra lavagna. Okay, so our goal is to derive the matrix element for the molar scattering. Let me write down first of all the Feynman diagram of this. Okay, that is you find already in the slide. So we have the incoming electron, the outcoming electron. This is the first vertex. That let's label this as mu. Then we exchange a photon. Then we have the other incoming electron, E minus. The other emitted electron, E minus. And then we have another vertex here that let's call this nu. And then we let me just write here the 4 momenta of all the particles here. So we have P1 for the first one, P2 for the second, P3, and P4. Okay. So for the moment, the Feynman diagram is not really relevant. Okay, we will use it in a proper way later on through the Feynman rules. But it is anyway useful to have it here just to follow the discussion. Okay. So let's now describe the interaction at the upper and the lower vertex. Okay, so the interaction at upper vertex that we called mu. Okay, so this is given by psi P3. Then we have our potential energy. Then we have psi P1. Okay, this we can also write in an equivalent way as the Hermitian conjugate of the spinor or the outgoing electron at the upper vertex, then the electromagnetic potential energy, and then the spinor for the incoming electron. Now let's substitute here all the pieces. Okay, so this is the Hermitian conjugate spinor for the upper final state electron. So this one, the posso usare il mouse. Okay, for this one here, P3. So this is gonna be U daga of the electron P3 times e to the minus I P3 x. Then we have the full expression of the potential energy that I just gave you in the previous slide. So it is minus E, which is the electron charge, gamma 0, gamma mu, the polarization vector of the photon, and then the plane wave of the photon, e to minus qx. And finally, we have the spinor of the upper initial state electron, which is UP of P1, e to the I P1 X. So let's label all these terms here. So this is the spinor of upper final state electron. This is the spinor of the upper initial state electron, and in between we have the potential energy. Okay, so if you remember, okay, yes, we will go on now. So now let's make some simple algebra. So this we can write as U E daga of P3. Then we collect here minus E gamma 0, gamma mu, epsilon mu, lambda, UE of P1. And then we collect at the end all the exponentials. So e to the minus I, P3x. Let me just remind you that Q is the transferred for momenta. So Q is P1 minus P3, okay? So it's P1 minus P3 corresponds to the momentum transfer, so the momentum of the exchanged virtual photon. So this is going to be times e to the minus I, P1 minus P3 x times e to I, P1 x. So one more passages just to be for completeness. So this, let's just copy all this part here. Minus e, gamma 0, gamma mu, epsilon mu, lambda, ue P1, and then this is going to be just e to the minus I, P3 plus P1 minus P3 minus P1 x. And so you realize that all these terms cancel. So this is just e to the 0 equal 1. So at the end, we express our interaction of upper vertex by this term here. So let me write down this again for completeness. So the psi P3 V psi P1 is going to be Q daga E P3 minus E gamma 0 gamma mu epsilon mu lambda UE P1. And then you do the same exercise for the lower vertex. Okay, I will not repeat the passages, but they are essentially the same. So for the lower, so this is upper, and for the lower, we're going to have psi P4 Vm psi P2, and this is going to be U daga electron of P4 minus E gamma 0 gamma nu, because now the lower vertex we called nu, okay, epsilon nu lambda star. This is the way to label, okay, the polarization vector at the lower vertex, and then mu e P2. Okay, so we've now expressed the full expression of the interactions at the upper and at the lower vertex. Allora, vi chiedo un attimo, riuscite a leggere bene quello che ho scritto?
Chi si vede?
Sì.
Sì.
Ottimo.
Sì,
C'è ancora qualcuno che deve copiare o possiamo andare avanti? Ok, andiamo oltre. La pagina 1. Okay, so let's now put everything together and calculate the matrix element, so the transition probability amplitude. Allora, questa adesso la devo togliere. Vediamo un po' come fare. Ok, vedete una pagina nuovamente bianca, giusto? Ok.
Vede bianco.
Ok, benissimo. Quindi andiamo adesso a pagina 2. Let's continue the derivation. So now we put everything together into the transition probability amplitude. So this is going to be psi p3 Vm psi p1. Then we have our bosonic propagator, 1 over q squared plus m squared. And then we have the third piece. You remember in the first slide I showed you that each diagram can be translated into a 3-piece for the transition matrix. Okay, so the interaction at the upper vertex, the bosonic propagator, and the interaction at the lower vertex. This is exactly what we are doing now. Okay, now we substitute what we have found and we sum over all possible polarization state. So this is the sum over all possible polarization state of the exchanged photon. And then we substitute the expression we derived before. So 3 minus E, gamma 0, gamma mu, epsilon, mu, lambda, QE, P1. Then, of course, the photon is massless, so we forget about the mass. This is just 1 over Q squared. And then we have U, E, daga, P4, minus E, gamma 0, gamma nu, is the lower vertex, epsilon, nu, lambda star, and U, E, P2. Okay, now we collect all the polarization vector into one single term. So this is going to be U, E, daga, P3. Also, we cancel the minus sign on the two electron charges. So this is E, gamma 0, gamma mu, U, E of P1. Here we collect the sum over lambda over epsilon mu lambda times epsilon nu lambda divided by q squared. And then we have the last term, that is U daga E of P4, E gamma 0, gamma nu, U E of P2. Now, let's write this in a more useful way. So we collected the charge at the beginning. Then this we write as U emission conjugate of P3 gamma 0. Let's close this parenthesis here. And then we are left with gamma mu UE of P1. Now remember that the sum of all possible final state at the two vertices is just the metric tensor. So it's minus G mu nu over Q squared. And here we have also E, and then we have U daga E P4 gamma 0, gamma nu, U E of P2. And now we are essentially done. Okay, let's collect this minus sign and the two electron charge here. So minus E squared. Now remember that when we multiply the Hermitian conjugate of a spinor right here with the gamma 0 matrix, we obtain the adjoint spinor here and there. So let's write this in terms of the adjoint spinor. So this is U bar E of P3, gamma mu, U E of P1. Then we have G mu nu over Q squared. And then we have the other term U bar, so adjoint spinor of P4, gamma nu, U E of P2. Now you realize that these two objects here and there are nothing else than the usual 4 currents, okay, that we studied already a lot, okay? So let's define the G electron mu as U bar E P3. So this is at the upper vertex, that's why we put mu here, of P3 gamma mu UE of P1, and similarly the J E nu, so at the lower vertex, as the adjoint spinor of P4 gamma nu, and then UE of P2. And so with these definitions, we can write our matrix element in a much more compact way. So the MFI is equal to minus E squared, and then we have J E mu, the metric tensor, J mu nu, J E nu, divided by Q squared. Then you probably remember from the first lesson, okay, that when you multiply a contravariant for vector with the metric tensor, you obtain the covariant for vector, so with the index below. So this is minus E squared J E mu J E nu. Now this is a covariant, and this the other was contravariant before, and again divided by Q squared. But then when you have this kind of syntax here, this is nothing else than the scalar product, as you know, right, from the first lesson. So this is just minus E squared JE scalar JE divided by Q squared. We can also put here just in parentheses mu and ni, just to remember that they refer respectively to the upper and the lower interaction vertex. Ok, ci sono domande su questo sviluppo che abbiamo fatto? Tutto chiaro?
Io ho una domanda, professore.
Dimmi.
Nel passaggio precedente
Sì.
non abbiamo messo l'indice mu perché vogliamo far vedere che quella corrente lì è calcolata nel vertice in basso, così come l'abbiamo fatto nel
Allora, aspetta, dove devo guardare? Dove devo guardare?
Dov'è il mouse?
Sì, qui?
Sì, e nel passaggio precedente, subito, a sinistra.
Qui.
Esatto.
Mm-hmm.
Quando facciamo la contrazione con G mu nu, in teoria comparirebbe...
Ah, scusa, hai ragione, questo è un mu.
mu.
No, hai ragione, questo è un mu.
Ok.
È questo che intendi?
Sì, esatto.
Sì, è chiaro, mi sono sbagliato.
Volevo capire se fosse un focalizzarsi sul fatto che una è calcolata da una parte e una dall'altra.
No, cioè formalmente è corretto come dici tu, è mu nu perché devi incontrare gli indici. Poi l'ho messo tra parentesi nell'ultimo passaggio, giusto per ricordarci che uno fa riferimento al... Potete anche ometterlo. Ok, grazie a te. Ok, allora, se non ci sono altre domande possiamo tornare sulla slide. Quindi questo lo tiriamo giù e qui adesso ci allarghiamo. Allora, vedete di nuovo la slide giusto in formato pieno, giusto?
Yes.
Ok. Ok, bene. Allora adesso quindi qui vi riporto sostanzialmente quello che abbiamo derivato adesso sulla lavagna. Ok, so you see here the two expression, okay, of the two interactions at the upper and the lower vertices. And then at the end, the expression that we derived, okay, here is written correctly, in fact, for the probability, so transition probability amplitude, okay, that at the end is corresponds to, okay, the square charge and the scalar product of the two currents at the upper and lower vertex. Now we can also write these in a more convenient way, and we will see why in a few minutes why it is more convenient. So instead of writing MFI, you multiply by minus I. Once you do so, okay, you can rewrite your transition amplitude in this way, okay, where you have the full explicit expression of the photon propagator with the minus I here, okay, the one that I provided in the previous, some of the previous slides. And you also have the full expression here of the so-called vertex factors. And this you will understand why it's important when we will repeat this calculation using the Feynman rules. Okay. So of course the two are exactly equivalent, but this gives you the structure that you can construct by using the Feynman rules, as we will see in a moment. Okay. Now, this is not the end of the story. Okay. Because the diagram that we just calculated, so essentially the transition matrix for this process, is not the only one for the molar scattering. Okay, the reason is that you have two electrons in the final state, so this diagram interferes with this other diagram, where the only difference is that the two final state electrons are interchanged. So the lower comes with the form momentum P3 and the upper with the form momentum P4. And since they are indistinguishable because the final state particles are the same, you have to take into account both diagrams and the interference between them. Okay. So how do we do that? We have to add another term for the second diagram into our transition probability amplitude. Okay. So the first term is the one that we just derived. The second term you can obtain from the first one by just interchanging the four momenta of the two final state electrons. Okay, so UEP3 become interchange with UEP4 and vice versa. And you have also to add a relative minus sign, okay, between these two pieces. Okay, and this is to account for the interchange of identical fermion, Dirac fermions. So this comes from the Dirac statistics. So this is the piece we just calculated. The other piece you just obtain from the first one by changing P4 with P3 and P3 with P4 in the numerator and the denominator, and adding here another additional minus sign. So you get now a plus sign here. This is the correct way to take into account both. Now, we want to calculate for the moment the unpolarized cross-section. Okay, so suppose that we don't have any information about the spin orientation of the incoming electrons and of the outcoming electrons. If this is the case, okay, then we have to average over all possible spin states of the incoming particles and to sum over all possible spin states of the final state particles. And when we do so, this we have seen already in the general theory, okay? If you remember, we obtain the spin average transition matrix element squared, okay? Where now we have the average over the initial state spin. So you sum over the initial state spin and you divide by the total spin multiplicity for the initial state particle, SA plus SB in general. And then you also have another sum over the final state spin, okay? And the argument is, of course, the sum of these two contributions. So once you compute this correctly, you are now averaging over all possible initial state and final state spin. So you end up with the unpolarized cross-section, okay? If, on the other hand, you prepare an experiment with a precise initial state spin of the interacting particle, and you are also able to measure the final state particle spin, then, okay, only one term, you don't have to sum all of them, of course, but only one specific spin combination will appear into your cross-section. Now, the last term is to put now our average transition matrix squared into the general formula of the differential cross-section that we derived starting from the Feynman-Golden rule, if you remember, okay? So here we have the S and S variable. These are the initial state and final state three momenta of the initial state and final state particle in the center of mass system. And then you have your spin average squared transition amplitude, okay? So this is the general formula for cross-section in the center of mass. And this is the end of the job for the molar scattering, okay? Now, we spent quite some time to do this, although it was quite interesting, I hope. So although deriving the expression of the transition amplitude for a given process from first principles, like we just did, so starting from the Dirac equation and then applying perturbation theory, is of course very instructive and provides a deep insight into the underlying physics, the calculation was quite involving, and this is considered a very simple first-order process. Okay, consider now you want to calculate a higher order process with 4 or 5 vertices from first principles. You can always do that, but of course will be a mess. Okay, the calculation will diverge. So that's the merit of Feynman, because Feynman introduced the Feynman rules that we will now see. Okay, and with that allow to calculate the same cross-section, so the same transition amplitude in a much simpler way. You just have to make use of these simple rules. Okay, But this is not a trick. I mean, the Feynman rules are formally proved in the framework of the quantum field theory. Okay, so is everything consistent? Of course, it is just an immediate way to obtain your cross-section. Okay, without having to start from first principles. So let's now discuss in detail how to make a Feynman diagram. Okay, so you see an example here on the top of the slide. So and so let's use this to introduce the Feynman rules also in the next slides. So you see there are straight lines and a wavy or curly or dashed line. In this case, it's just a wavy light. So the solid solid straight lines represent fermions, either leptons or quarks. Okay. While the wavy or curly or dashed lines, depending on the interaction, represent the boson. Okay, so for the electromagnetic interaction, we have the photon, and the photon is represented usually by this wavy curve. Now, by convention, time increases from left to right. Okay, so this is the initial state, and this is the final state. Now, what about the arrows we have here? An arrow indicating a motion of a particle backward in time, like this one, or that one, okay, indicates an antiparticle, okay, moving forward in time, and thus represent a real antifermion. So in the Feynman diagrams, the old convention is used where antiparticles should move backward in time, but this is only a way to represent them and to distinguish them from particles. So particles have the arrow in the direction of time, antiparticle in the opposite direction. But the Feynman-Stackelberg interpretation is still valid, okay? So these are not moving backward in time. That's the way to represent them. Instead, they are antiparticles moving forward in time. Okay, so really physical antiparticles, antifermions. Now, fermion and boson lines match at vertices. There are two vertices in this simple diagram, where the charge, so electric charge, energy, and momentum are conserved. Okay, so at each vertex, charge, energy, momentum are conserved. Now, lines entering or leaving the boundaries of the diagram represent on-shell free particles. So in this example, this one, this electron, this positron, this whatever, this quark, and this antiquark, and this quark. So these represent on-shell free particles, so real particles. While lines joining the vertices, like the photon in this example, so joining one vertex to the other, represent virtual particles or off-shell particles. And this could be boson, but it can also be fermions. You can also have diagrams where we exchange virtual fermions, as we will see. Okay. And since they are off-shell, okay, their mass does not correspond to that of the corresponding real particle, because the relativistic energy momentum relation is not fulfilled for off-shell particle, if you remember. Okay, we discussed this at the beginning. So in principle, you know, real photons are massless, but due to this non-energy conservation in this virtual process, the virtual photon can be even massive, okay, because it is allowed to violate the relativistic energy momentum relation. Now, the strength of the interaction is represented by the coupling constant, okay, that for the case of electromagnetic interaction is the fine structure constant, okay. So you see that at each vertex, the strength of the interaction is proportional to the square root of the fine structure constant. And the square root of the fine structure constant is proportional to the electric charge, the electron charge, okay? Indeed, the square root of the coupling constant are involved at the vertices, while the propagators, okay, are associated to the virtual particles which are exchanged between vertices, okay? So here we have the strength of the interaction at the vertices, and here we have the propagator for the boson, for the exchange of the boson. Now, in QED, the fundamental interaction is between a single photon and two spin-half fermions, either leptons, charged leptons, of course, not neutrinos, or quarks. And there is no QED vertex connecting more than 3 particles. Okay, this you cannot have, never. Now, having understand how to interpret, okay, the symbols in each Feynman diagrams, let's now make the step further. So let's see how to connect the symbols to pieces of our matrix element, so our transition amplitude, okay? So have you seen the external, so the time always runs from left to right. The external solid line or curvy line represent real particles, So these are real fermions or antifermions. And you see here the corresponding spinor of adjoint spinor. And you see also the case for real photons. Okay. So these are objects that leave the vertex and go outside of the diagram. Then we have the propagator for the internal lines. We have the photon propagator, which we just studied. So minus Ig mu over q squared that connects two vertex. But we can also have fermion propagator. So we can exchange an electron, a neutrino, whatever here. Okay. And of course, the propagator now is a little bit more complicated because we also have to take into account the mass of the fermion, either in the numerator and the denominator. Okay. And then finally, at each vertex, you have the so-called vertex factors, okay, which are given by minus I, then q times the electron charge. So this is exactly 1 for an electron, or 2/3 for an up quark, or minus 1/3 for a strange quark, okay. And then you have gamma mu. So these are all the ingredients and of the matrix element and how they are connected to the symbols in the Feynman diagrams. Okay, so this is the way to translate the Feynman diagrams into the ingredients of the matrix element. This is what we really do when applying the Feynman rules. Okay. Now, again, associated with each vertex is the cupping constant. Okay, it is not reported here, but essentially it is encoded in the vertex factor, which is proportional to the electron charge. So you find it here, which indicates the probability of the emissions or absorption of the particle, and thus the strength of the interaction at that vertex. Now, one more argument about Feynman diagrams. So Feynman diagrams not only account for the summation over all possible polarization state of the exchange virtual particle, where this sum enters in the definition of the photon propagator, as we've seen, but they also account for all possible time orderings. What does it mean? So let's consider these two processes. So it is still electron-electron scattering. Okay, consider that as usual time runs from left to right. And let's try to interpret these two processes, okay, in terms of the chronology of what is happening. So let's consider the first diagram. Okay, the first diagram, the first thing that happens is that, so time is running in this direction. The first thing that happens in time is that the lower electron emits a photon. And then at a later time, this photon is absorbed by the upper electron. And overall, there has been a momentum transfer between the two electrons. Okay. Now let's consider the second diagram. The second diagram, the chronology is opposite, okay? So the first thing happening is the upper electron emitting a photon, and then afterwards, a lower electron absorbing the photons. And so these are two different time orderings for the same process, okay? Now, what is the point here? The point is that since the exchanged virtual photon is not observable, it is virtual, so it's off-shell, you cannot never see this, only the combined effect of all possible time ordered diagrams is physically meaningful, is real, okay? And so only the combined effect of all possible time orderings is provided by the real Feynman diagram, okay? So the real Feynman diagram is actually the sum of all possible time orderings. And this is represented by this diagram here, where now the left-hand side, okay, represents the two initial states, and the right-hand side represents the two final state particles, without specifying which particle emits and which particle absorbs the photon, because you never know. You can never measure this, okay? Okay, now we have all the ingredients, and to start the calculation of the, again, the matrix element for the molar scattering, but now using the Feynman rules. Of course, we end up with the same result that we obtained before, starting from first principles. Okay. So I divide these into steps. So the step one is the following. For any process of interest, such as the molar scattering, for instance, draw a Feynman diagram with the minimum number of vertices. Okay. In this case, we have only two. Minimum number of vertices means the lower or the lowest order diagram for this process. Of course, as we will study tomorrow, you can have infinite higher order processes. And there may be more than one. Okay, we know, for instance, that for the molar we have this one, but we have also the other one where the two final state electrons are swapped, okay, because they are indistinguishable. So this was the first step. Now the arrows are only drawn on external lines. Okay, this we know from the Feynman rules, and represent the particle flow. which is always forward in time, or anti-particle flow, which is backward in time, as it is represented, not here, but in the previous one you've seen. But they do not represent the momentum flow. This just means that the momentum is always, of course, positive, okay? And so all particles and antiparticles are always moving forward in time, okay? And this is just a trick to distinguish them in a Feynman diagram. Now, the second step. For each Feynman diagram, label all the four momentum entering into the game, and then force the four momentum conservation at any vertices. So we put here P1, P2 for the initial state electron, P3 and P4 for the final state electrons, okay? And then, of course, for momentum conservation requires that the momentum of the photon, is Q, is given either by P1 minus P3 or P2 minus P4. Okay. Now, step 3. Every QAD vertex contributes with a vertex factor defined in this way in general. So minus I, GE and gamma mu, where GE is a dimensional coupling constant for electromagnetic interaction, which is, of course, related to the defined structure constant. So alpha is essentially GE squared over 4 pi. So it turns out that GE, so the coupling constant of the electromagnetic interaction, is proportional to the square root of alpha, and so it's proportional to the electron charge. So for the diagrams where we have electrons, okay, we can write our vertex factor as IE gamma mu, okay, which we use here the charge of the electron, which is minus C. So the minus cancel with this minus, and then we just get the electron charge here in natural units. Okay, so this is the way we will represent. This is the generic way to represent the vertex factor in QED, and this is the way we will use it when we exchange object with the electron charge. Of course, this does not apply for quarks, because quarks have a fractional charge. So you have to put a fraction here, either 2/3 or minus 1/3. Now, in the language of quantum field theory, okay, let's make now a bridge again with quantum field theory. The process occurring at the vertices is interpreted as following. So the initial electron field is destroyed by an annihilation operator and disappears at the vertex. And at the same time, the creation operator creates a final state electron field and the photon field. Okay. So what happened in this vertex here is that the initial particle is destroyed by an annihilation operator, and then a creation operator will create a two-particle state, which is the final state electron and the emitted photon, and the same at the other vertex. And asking whether the initial or final electron are the same or different particle is meaningless, because all electrons are identical. Okay, so this is the way you would interpret this, let's say, perturbative approach in terms of the quantum field theory language. Now, step 4. Each vertex contributes with a fermion current. Okay, so now you have your vertex factor, as defined before, and then you enforce the spinor and adjoint spinor in order to construct for each vertex the corresponding 4 current. Again, we are labeling mu and nu to distinguish the upper and lower. So this is a J mu E and a J nu E, where the Lorentz index mu and nu appear here. Okay, and then the last piece is adding the photopropagator, which is minus I J mu over Q squared. Okay, so now we have really everything. Okay, so we translate every piece of our diagram into a piece of our matrix element, and we just have to put everything together. Okay. There is just a note here that for the fermion, the propagator is more complicated, as we have seen before. Okay. So now we put all our 3 ingredients together, and so we obtain the minus I multiplied by our transition probability amplitude as the current at the upper vertex, the propagator of the exchanged photon, and the current at the lower vertex. And then if you also want to divide by minus I, you obtain the full expression of the transition matrix element. Okay, so we get exactly what we derived before, starting from first principles. Okay, but here we don't have to make any calculation. We just have to translate each piece of the diagram into a piece of the matrix element following the final rules. Okay, and so once you get practice of these, you see how this is simple and how you can really make complicated calculations, so complicated processes with many vertices in this straightforward way. And this is the merit of Feynman, and one of the reasons he got the Nobel Prize. Okay. Now, of course, we can also go further here. Okay, so these are the two currents. We can again make use of the tensor matrix, the metric tensor. So again, we end up as before the scalar product of the two currents, and realize that the transfer momentum is nothing else than, for this specific diagram, is nothing else than the T Mandelson variable. Okay, so it's P1 minus P3 squared, which is exactly T. Okay. So overall, we managed to calculate the transition amplitude for the same process, which is the most simple electromagnetic process, smaller scattering, starting from first principles and applying the Feynman rules. Then, of course, also here you have to take into account the other interfering diagram. You have to put the two things together. You have to make average over the spin, initial spin state, and sum over the final spin state, and put everything into the reverse section form. Okay. Now, this is about the molar. So let's consider now a different process, that is the electron-positron annihilation into a muon pair, mu plus mu minus pair. What is the difference here? The difference now is that you have particles and antiparticles. Okay, this is the positron, the antiparticle of the electron, and mu plus, which is the antiparticle of the muon. And so now you have to use the antiparticle spinor V. Okay, for the antiparticle, and the particle spinor U for the particle. So if you now apply the Feynman rules for this simple process, okay, you're gonna derive this expression here. You can do by exercise, okay? So we have now the current at this vertex here, where we now have a positron with P2 momentum. So it comes with an antiparticle spinor, and an electron with P1, which comes with the particle spinor. And then similar for the final state, okay? And then also this we can later express as the scalar product of the two currents. Okay. Now the question is, how do we know if we have to put here the as an adjoint spinor the particle or the antiparticle? What about here? So what is the rule to decide if here I should put the antiparticle spinor or the particle spinor? And the rule is given by this simple mnemonic rule. Okay, so you follow the arrows of your diagram. Remember that the particles are drawn with according to the time flow. Okay, and antiparticle opposite, so they move like if they would move backward in time. So, for instance, at this vertex, the current flow is like this, from top to bottom. Then you take the opposite. So look this red arrow. So you take the opposite, so you start from bottom to top, and when you do so, the first object you find, either it is a particle or antiparticle, this should come with the adjoint spinor. And you do the same also here, okay? So the rule is the following. The first particle encountered when following a fermion current from the end to the start, so in the opposite way, in the direction against the sense of the arrows, this will always appear as an adjoint spinor in your matrix element. Okay, so with this mnemonic rule, we also eliminate this ambiguity, and we can also write the transition probability in the proper way. Okay. Ok, sono le 10, facciamo una pausa di 5 minuti, c'è ancora parecchio materiale da dare, quindi ci vediamo alle 10:20. Ok?
Va bene?
Ok, va bene.
Ok.
Ragazzi, ciao a tutti, scusate, ma gli dobbiamo mandare la mail? No, non ho mica capito.
Sì, ragazzi, mandatemi la mail così ricevo i vostri indirizzi e
Ok,
mi fate
mi
la
scusi,
verifica.
non avevo capito solo che se qualcuno aveva la registrazione gliela doveva mandare, non avevo...
Quella è un'altra cosa, se qualcuno ha la
Ok,
registrazione
perfetto,
va bene, però comunque tutti mandatemi una mail così ho tutti i vostri indirizzi.
grazie mille.
Grazie. Ok, riprendiamo? Siete tutti? Mi sentite?
Sì, sentiamo. Non so se ci
Ok.
siamo tutti.
Sì,
A me si sono tutti, poi se siete presenti. Ok. Va bene, allora, quindi torniamo adesso, faccio di nuovo lo sharing del desktop. Ok, adesso dovreste vedere di nuovo il mio desktop e in particolare dovreste vedere la slide 20, giusto?
Sì, sì, si vede.
Ok,
Sì,
benissimo.
slide 20.
Ok, quindi abbiamo discusso, diciamo, abbastanza in dettaglio lo scattering Moller, abbiamo visto come ricavare la sua elemento di matrice, quindi insomma, la densità di probabilità in due modi, partendo da principi primi e utilizzando le regole di Feynman in modo molto più semplice, e poi ovviamente diciamo, lo step successivo è quello di introdurre, di mediare sugli spin, introdurre il tutto all'interno della forma della sezione d'urto, sia quella differenziale, e poi eventualmente integrare sull'angolo solido e ottenere la sezione d'urto totale per quel processo. Adesso, diciamo, per adesso ci dimentichiamo dello scattering Moller e passiamo a un altro processo che abbiamo già iniziato anche a vedere poco fa, che è appunto la annichilazione E più e meno in una coppia mu più mu meno. E utilizzeremo questo processo per introdurre adesso diciamo, un fatto nuovo, che ovviamente si applica anche al caso dello scattering Moller, ma lo applicheremo, diciamo, utilizzeremo questo processo, che è appunto la conservazione delle elicità nelle interazioni elettromagnetiche. Okay? Quindi vediamo come, diciamo, quali sono gli effetti di questa conservazione, che abbiamo già imparato a studiare ragionando diciamo, in generale con la teoria di Dirac per le quadricorrenti. Okay, so now let's switch to English. In calculating the cross-section of a given process, so let's take as an example the E plus E minus annihilation into mu plus mu minus pair, the transition matrix has to be evaluated taking into account all possible spin states of the particles involved. Okay, so let's consider the initial state. In the initial state, we have a positron and an electron, but each can have two possible spin projections. Okay, let's say spin up and spin down. And so in total, you have 4 helicity combinations for the initial state. Okay, so the small arrow is the spin and the long arrow is the momentum. Okay, so you see here the two are parallel, so you have a positive helicity. Here they are anti-parallel, you have a negative helicity. So this first combination is plus minus. Then you also have plus plus, where the two are both parallel, or minus minus, both anti-parallel, or minus plus. Okay. So in total, you have 4 different helicity combinations for the two initial states. And of course, you have also 4 possible helicity configuration for the final state, because the same applies to the final state of muons. Okay. So in total, you have 16 possible orthogonal helicity combinations, each of which constitutes a separate physics process. So as an example, E plus into mu plus, E plus into mu plus mu minus, etc. Okay, you have 16 of these terms, which all contributes to your process, okay, overall. Okay, now, and as a consequence, for a given initial state, so for instance, for the plus plus initial state, so positron plus, electron plus, there are 4 possible final state configurations, okay? So if you calculate the transition matrix squared for the plus plus case, this refers to the initial state only, then you have the 4 possible final state helicity combination. So plus plus into plus plus, plus plus into plus minus, plus plus into minus plus, plus plus into minus minus. And then you have also the 4 initial states. So you have 4 of these, in total 16, in fact, okay? Now, if we do not select the polarization of the initial state and final state particles, we have to average over the polarization of the initial state particle and sum over the polarization of the final state particles, okay, as we've done before. So, in fact, in most of the electron-positron colliders, the colliding particles are unpolarized. This means that the 4 initial state helicity configuration are all equally probable, okay? And so if this is the case, so you are not selecting a specific spin state, or in other words, a specific helicity combination, then you have to, again, average over all of them. And this is the way we are used to do so, okay? So we average over the initial state, so we sum over initial state, and we divide by the initial state multiplicity. And then further, we sum also over the final state spins. So if you put now the spin of an electron and positron, which is 1/2, okay, this whole term here will reduce to 1/4. And then here you are summing up all the possible terms, where each of these has 4 different possible final state configurations. Okay, so these are again 16 terms essentially. Now, let me now remind you with this slide what we have learned about chirality conservation. Okay, So chirality is conserved in all electromagnetic processes. And as a consequence, as we have seen, vector currents made by two particle spinors, so U, or by two antiparticle spinors, V, are zero for the case with mixed chirality. If you remember, we show that, let me start from the beginning. So this is your 4 vector current, okay? This is the case of two particles, so adjoint particle spinor and particle spinor. You can always split each of them into a left-handed and right-handed chiral spinors, okay, which are simultaneous eigenstate of the Dirac-Hamiltonian and the gamma 5 chiral operator, if you remember. Then you take the products and you end up with 4 different terms. And then we show in the blackboard that the mixed terms, so left-right or right-left, are equal to 0. And the only ones surviving are those with not mixed terms, so the pure left-left or pure right-right terms. Okay. And now in the ultra-relativistic limit where you can neglect the mass, so this is always true because this is about chiral states. Okay. But in the ultra-relativistic limit where you can neglect the mass, this is approximately true also for the helicity, because if you remember, if you can neglect the mass, helicity eigenstates coincide with the helicity, with the chiral eigenstate, and the helicity operator coincides with the chiral operator in that limit. Okay. So in the ultra-relativistic limit, we can also write our vector current as u bar minus gamma mu u minus plus u bar plus gamma mu u plus. Okay. So these two are 0, and now we are translating from chiral state, left and right, to helicity state, minus and plus. Okay. And this is, this I think I already showed you before. Okay. So when you look at these interaction vertices, these are the only possible helicity combination. Okay. For fermions, either they are both positive, so spin and momentum are both aligned, or they are both anti-aligned. Okay. And then similar here for the antifermions. So the helicity of the particle leaving the vertex is the same as that entering, always. Okay. Now, let's now extend this argument to the case of annihilation of pre-production processes, such as the one we are studying now. So E plus E minus into E plus E minus. And the difference now is that one have in this process not only particle but also antiparticle. So it's a combination of antiparticle and particle spinors. Okay, whereas in the example before, they were either only particle spinors or only antiparticle spinors. Now we have a mixing here because this is an annihilation process. So this we will not show, but you can prove yourself using the same algebra we did essentially on the blackboard, that in this case, where we are now mixing antiparticle spinor with a particle spinor, so you can also always decompose it this way, then in this case, the pure terms cancel, so they are exactly equal to 0, and only the mixed term will survive. And then again, in the ultra-relativistic limit, we can translate these chiral states into helicity states. And so essentially our vector current for the case of annihilation processes, so with the antiparticle spinor and the particle spinor, will only have mixed helicity terms. Okay, either this or this. And this is the situation now, the analogous situation for the annihilation processes. Okay, so it turns out that the incoming or outgoing fermions at each vertex have now opposite helicity. So this is positive helicity because the momentum spin are aligned. This is a negative helicity because they are anti-aligned. Okay, or vice versa, and same also for the final state particles. Now, what about all the other possible combinations? Well, all the other possible combinations are 0. So these are the only two surviving. Here, I also put the case where you have both particle and both antiparticle or mixed. Okay, so all these other helicity combination corresponds to a null current. The only ones surviving for this case are those here. And this, of course, has an impact, okay, in the cross-section, okay, when evaluating the cross-section, because only few currents will survive out of the total of 16 possible combinations, right? So in the ultra-relativistic limit, where we can neglect the mass of the electron and also the muon compared to the energy, chirality conservation implies that only 2 of the 4 helicity combinations for both the initial and the final state lead to non-zero currents, which are those coming with the mixed terms, in fact, plus minus, minus plus for the initial state, and plus minus minus plus for the final state for the muons. Okay, so these are the only 4 surviving currents. Where let me just remind you that U plus, U minus, V plus, V minus are nothing else than the helicity spinors that we already introduced in the Dirac theory. Okay, we didn't derive them in terms of the cos theta and sin theta or angle phi, but this I showed how this comes really from the use of the scalar products. Okay. So these are simultaneous eigenstate of the Dirac Hamiltonian and the helicity operator. And in the limit of negligible mass, these are also eigenstate of the chiral operator. Now, so this is the situation for the E plus E minus into mu plus mu minus process. Okay, so only 4 helicity combinations will give non-zero matrix element and will thus contribute to the cross sections. So let's consider the first one. Okay, so this is in the center of mass. So we have 2 interacting, so an electron with a positron coming the opposite way. This is the case plus minus, where so the electron has a positive helicity, momentum and spin are aligned, and the incoming positron has negative helicity because spin and momentum are anti-aligned. In the final state, we have a positive helicity for the muon plus and a negative helicity for the anti-muon minus. Okay, and similarly, you can construct all the other 3 allowed combinations. All other combinations are 0. They do not contribute to the cross section of the process. Let me also note that in all cases, the spin of the initial state and of the final state particles are always aligned. You can see here, okay? Both to the right or both to the left, and same also for the final state. And this is, of course, expected because in the process, a photon is exchanged, okay? And a photon is a vector boson, so it comes with a spin 1. And so you need to have the spin 1 or spin minus 1, of course, in the initial and final state in order to have, let's say, angular momentum conservation fulfilled. So now let's write down the matrix element squared in the full glory, okay? So this is averaged already over the spin. And so we have indeed 16 terms. Most of them cancel because of helicity conservation, so chiral conservation essentially in electromagnetic interactions, and only 4 of them will survive, okay? So overall, this is, oh, I need to close the parenthesis here. So overall, this is the average square transition matrix element, okay, with only 4 mixed terms surviving: plus minus to plus minus, plus minus to minus plus, minus plus to plus minus, minus plus to minus plus. And each of these terms, of course, is written in the usual way. Okay, so we have the square charge, the minus sign, the Mandelstam variable, either S or T. We will see then how to distinguish between the two, and then the scalar product of the 2 currents at the 2 vertices. Okay. So each of these terms come in the usual form that we derived. Now, if you now use the full expression of the helicity spinors, so those that I've shown here, okay, that comes in terms of this theta and phi angle, and you perform the scalar product of the 4 currents, those here, then one can show that these 2 objects are the same. So m plus minus to m plus minus is equal to m minus plus to m minus plus, and they both are equal to, let's say, essentially the squared fine structure constant, and then 1 plus cos theta squared, where theta, okay, is the polar angle between the outgoing muon with respect to the incoming positron in the center of mass system. And the other 2 are also equal, plus minus into minus plus or minus plus into plus minus, and they come with a 1 minus cos theta term squared. Okay. Since we need 4 of them, of course, we have to add them. Okay, we can then we add so twice each of these contribution. We make some simple trigonometric formula, and at the end, our squared average transition matrix amplitude is given by e to the 4th 1 plus cos square theta. Okay, so this is, let's say, also the angular distribution we expect for our final state particles. We can always rewrite our matrix element in terms of the Mandelstam variable. Okay, so you just need to substitute to remember that S, T, and U are defined in this way. Okay, and then you write your momenta in spherical polar coordinates, okay, and then it turns out that this is exactly equivalent to this one, okay? So t squared plus u squared divided by s squared. We will not show these, but it's trivial by essentially you just have to substitute the momenta and write them in the polar coordinates. So now let's put everything together into the cross section. So this is the differential cross section for the E plus E minus into mu plus mu minus annihilation process. We have the standard general formula here. So we put now here our expression for the squared average matrix element, which is e to the 4 1 plus cos squared theta. Okay. Okay, we can make also some simplification here because, of course, you can write the electron charge in terms of the fine structure constant always. Okay, so at the end you obtain this expression here. And here we also, in the hypothesis that we can neglect the mass of the electron and the muon, so in the both in the initial and final state, these two becomes approximately equal, so we can also drop them from the formula to a very good approximation. And so let's now see what is now the angular distribution of this cross section. Okay, so this is the behavior of this 1 plus cos squared theta as a function of cos theta, and you see here also the two contributions, okay, that we showed before, that of course have to be added together in order to get the total contribution here. Now the question is, so there were a lot of theory here, a lot of assumptions. What about now experimental data? I mean, siamo sicuri che tutta questa cosa complicata che abbiamo fatto in realtà ha un riscontro sperimentale? Allora, the answer is yes and no, or actually absolutely yes. What I mean here. So this solid curve here is exactly this one. Okay, so it's the expected 1 plus cos theta, cos squared theta. Okay, and the dot are experimental data by the Jade experimental pattern daisy from essentially the 80s of the last century. Now, more or less, the trend is okay, but it is not completely okay. Okay, you see that the data follow much better this dotted line. So is this a success of the theory or say a disaster for the theory? Well, it is a success at the end because we have to take into account that the same process, so electron positron into mu plus, can come at high energy or from in two different ways. From the exchange of a virtual photon, which is the pure QAD process, but also from the exchange of a Z0, which is the neutral current boson of weak interactions. You see, the initial state and final state are the same. So this will be studied, of course, at the proper time. But you have to understand that these two processes, of course, interfere. Okay, so as soon as you rise with energy, you have to take into account also this diagram here in your calculation. And once you do so, you obtain the dotted line, which matches very nicely the experimental data. So this is actually a double success. Okay, is essentially a proof not only of the QED but also of the weak interactions. Now, the importance of this term is extremely low at low energy. So at low energy, essentially this process only occurs through electromagnetic interaction, but then this becomes more and more important as long as you increase the energy. And in particular, when the center of mass energy is of the order of the mass of the Z0 boson, so order 90 GeV, then this term here is absolutely and totally dominant, as we will see, because the Z0 comes as a huge resonance, and so this energy, the electromagnetic contribution is completely negligible. Okay, and then when we move to even higher and higher energies, the importance of the two becomes essentially the same, and this is, as we will study at the end, the essence of the electroweak unification. Okay, so the fact that electromagnetic and weak interaction are not indeed separate, different interaction, but they are essentially, they come from the same unified electroweak interaction that manifests itself only at high energies. Okay, so everything is understood concerning the E plus E minus to mu plus mu minus process. Okay, we can do the final step, sorry. We can now calculate the total cross-section by integrating the differential cross-section over the full solid angle, okay? So if you just integrate these angular dependence of over the solid angle, you end up with 16 pi over 3. Okay, we'll not show this, but just trust this. And so now you obtain at the end this very simple and predictive expression for the total cross-section as a function of the Mandelstam variable S, or if you like, as a function of the squared center of mass energy. Okay. If you now express this cross-section in nanobarns and the center of mass squared energy in Jeff square, then all these constants end up resulting in 86.8. Okay. So if you have just a constant, you change your energy and you obtain the values of your cross-section in nanobars already, but using this extremely simple relation. Again, how do we compare with experimental data? Very, very nice. Okay. So this solid curve here is given by this function here as a function of the square root of s, as you can see here. And these are experimental data coming from different experiments that are shown here. And also consider that this prediction here is based only on the first order calculation. So so far we only use the first order E plus, E minus Feynman diagram. But as we study tomorrow, in principle, you have infinite higher order contribution to take into account. But already at the first order, you see here that the agreement with experimental data is incredibly high. Okay. Now, so so far we studied in detail the molar scattering, so E minus E minus into E minus E minus, and the E plus E minus annihilation process into muon pair. So this you have to know, ok, quindi diciamo, ai fini poi diciamo, dell'esame, eccetera, diciamo, questi due vi chiedo di studiarveli bene, di saperli bene, se ve li chiedo dovete saperli spiegare più o meno come ve li ho raccontati io. Quelli che vedremo adesso invece è una carrellata di altri processi di QED, ok? Dove il calcolo dell'elemento di matrice è molto più complicato, per cui io ve li do adesso diciamo, per informazione vostra generale, okay? Per conoscenza generale propria, ma è qualcosa che non vi chiederò all'esame, anche perché appunto le espressioni diventano più complicate e difficili da ricordare. Okay? Quindi cominciamo a analizzare il Baba scattering. So the Baba scattering is now elastic scattering between an electron and positron, okay? Again, mediated by a photon. And this comes with two different diagrams, both at first order, okay? So in your total calculation, you have to take into account both, okay? And the fact is that having the same final state, so an electron and a positron, these two diagrams, of course, interfere. So you have to take them into account both. Now, the matrix element for the first diagram is equivalent to what we already derived for the annihilation process before, right before. The only difference is that we have now an electron-positron pair instead of a muon-antimuon pair. But everything is exactly the same, okay? What about the second, okay? The second instead is analogous to the one we calculated for the molar scattering, okay? You see here that this is the matrix element for the molar scattering, essentially. The only difference is that now we have not only electrons, but electrons and positrons. So you have to take into account also in the lower vertex the anti-particle, the anti-fermion spinor, okay? Then the structure of this probability amplitude is exactly the same of the molar one. And then of course you want to add them properly, and this comes with a minus sign to take into account the requirement of Fermi statistics, okay? Because these are essentially identical fermions. So you have to take, so the proper way to sum these two contributions is with a minus sign here. What about now the helicity, the allowed helicity combination? I mean, allowed by helicity conservation in QED, okay? So in this case, we have 6 different helicity combinations surviving, and all the other are 0, okay? So plus plus into plus plus, plus minus into plus minus, plus minus into minus plus, minus plus into minus plus, minus plus into plus minus, and minus minus into minus minus. And this is the way the two diagrams contribute to these helicity terms. So for the first one, we have only contribution from the second diagram. From the second one, we have a contribution from both diagrams, and so on, okay? And then, of course, in your spin averaged squared transition matrix, you want to have all these 6 non-zero contribution summed together, okay? And again, you can, this is okay, you can always translate these in terms of the Mandelstam variables, okay? So a compact way to express this matrix element after some algebra, of course, which is trivial, but we don't need to waste time on this, is to write down these in terms of the S, T, and U Mandelstam variables. And here one recognizes the pure term from the first diagram, the pure term from the second diagram, and the interference term, okay? Now, since in the center of mass frame, one can always express the t and u in terms of the polar angle this way. Okay, don't waste time to details. Let me just tell you this. Then you can substitute the expression of the three actually Mandelstam variable in terms of this theta and cosine and sine of theta angle in this expression before here. Okay. And once you do this, you make also some simple trigonometry, you end up with this expression for the differential cross-section, okay? Which has this, let's say, non-trivial angular dependence. How does this compare with the experimental data? It does very well, okay? So the experimental data, the standard model with running alpha, this we will understand tomorrow, but the correct one is the solid line. You see that it matches very nicely, impressively well, actually, the experimental data, okay? Consider here we have 3 order of magnitudes, and the agreement is perfect everywhere. Now, the agreement is so good, actually, between the QED prediction and experimental measurement, that this process, so the Baba scattering, is quite often used to determine the beam-beam luminosity in E plus E minus collider, or the beam target luminosity in fixed target experiment with positrons. Okay, so essentially you normalize your measurement to this very, very well-known cross-section, and this provides you a very precise measurement of the luminosity. Okay, and this you need in order to make absolute measurement of cross-section in experiments. Okay, so this was the Baba. Let's now go to the another process. This is the Compton scattering. So Compton is, as you know, interaction between a real photon with a real electron. So in this case, the topology of the diagram is quite different because we have real electrons, real photons, and a virtual electron is exchanged here. Okay. So the process includes real photons and a virtual electron, and this is the propagator for the virtual electron, which is exchanged here. Okay, so which also includes the mass term. Now, real photons are described by this plane wave now. So these are real photons, not anymore virtual photons. So you have the standard plane wave and the polarization vector. And when you put these into the matrix element, okay, you end up with this expression here. So you have the spinor of your incoming electron here. You have the wave function of your photon. Essentially, these term cancel from the in the two vertices. So you only end up with the 4 vector of the polarization state. You have your vertex factor for the this vertex here and the vertex factor for this other vertex there. And in between, you have this complicated fermion propagator, electron propagator. But again, you can exchange the two photons because they are indistinguishable. So you have another diagram contributing to the Compton scattering where the two are exchanged, okay? And so again, you have to sum up the two contributions. This is now the matrix element for the second term. Essentially what is changed is that you have to interchange now the current, the form momentum of the two photons, essentially. So the wave function of the two photons. And so you obtain this one by just exchanging these two terms here. And then the K epsilon and K epsilon prime are the momentum and spin state of the incoming or outgoing photon. Okay. So now we have an expression of these two matrix element of these two diagrams. You put them together, you sum them, you square, you take the average of the spin, and this is the expression in terms of the Mandelstam variable. Okay, minus U over S minus S over U. Well, and this is the expression of the S and U Mandelstam variable in terms of the electron momenta. Okay, electron photon moment. Yes. Now, last step is again to integrate over the full solid angle, and you obtain this prediction, okay, for the Compton scattering cross section. Okay. So once more, you don't have to. I mean, per l'esame, insomma, sappiate che esiste questo, però insomma è una cosa che non vi chiederò. What about now the E plus E minus into gamma gamma annihilation process? Okay, now we have an electron positron give rise to a photon pair. Again, we have two contributions because the photons are indistinguishable, and again we have a fermion propagator in between. Okay, so we do the same exercise. The derivation is quite complicated. You find it if you want for curiosity in Alzen-Martin. And you end up with this squared matrix element in terms of the Mandelstam variable. These you put once more into the cross-section, you express the momenta in terms of polar coordinates, and you end up with this expression for the differential cross-section that you want again to compare with experimental data. So here the comparison is done at different center of mass energy. So you see the square root of S. The square root of S goes like increases from top to bottom, and you see how well the experimental data agree with the pure QED prediction at first order. Okay. Now let's spend the last 5 minutes for this consideration. So I just show you the Compton scattering and the E plus E minus into photon annihilation process, and these are the two expressions that we derived. Now, by looking at the Feynman diagrams or by looking at the corresponding matrix element, you see that the two are, of course, topologically linked. Okay, so the diagrams of the two processes appear essentially 90 degrees rotated each other, and the corresponding spin average square matrix elements are identical apart from the interchange of T with minus S. Okay, so if you make this change, you obtain one from the other. If you rotate this by 90 degrees, you obtain this other. Okay. So there is, of course, a link between the Compton scattering and the E plus E minus annihilation process into photon pairs. And this link is a consequence of the so-called crossing symmetry that we will discuss now. And it is a more general effect, of course. So let's start this considering these two diagrams. Okay, so these two diagrams represent different processes. The first one is E plus E minus annihilation into a generic fermion-antifermion pair, be electron-positron, mu plus mu minus, quark-antiquark, whatever you want. And the second one is instead electron-fermion scattering. Okay, so the two, of course, describe different physical properties. But again, as you can notice, the topology is very similar. Okay, each of them can be approximately obtained by rotating the other by 90 degrees. And the currents involved in this process correspond each other after this simple substitution. So UP1 stays UP1, V bar P2 becomes U bar P3, U bar P3 becomes U bar P4, VP4 comes UP2. Okay, and this corresponds to the following changes in the Mandelstam variable. So S changes to T, T to U, U to S. Okay. So essentially, if you rotate this diagram by 90 degrees, you make these changes here in the four momenta, in the spinors, or equivalently, you make these changes here on the Mandelstam variable, you would obtain the other process. So the two are again strictly linked to each other. Now, the process like these, okay, like the first one, are called S channel, and the process like these are called T channel. And the name is not random, but reflects the fact that the propagator depends either on the T or on the S Mandelstam variable. So the propagator of the S channel, okay, is minus I G mu nu over S, where S is the sum of the two for momenta, P1 and P2. So you are summing these, okay, and this gives you the total momentum of the exchanged photon. Whereas in the T channel, we have the transfer momentum, so P1 minus P3. This gives you the momentum of your photon, and so this is the T Mandelstam variable. Okay, so essentially one divided the diagrams with these different topology in S channel and T channel. Okay, and this is the kind of squared for momentum entering into your propagator, respectively. Now, the electromagnetic process whose Feynman diagram are 90 degrees rotated. Okay, that means that they are in S channel and in T channel, respectively, can be coupled through this crossing symmetry. So the topological similarity of their diagrams is reflected at the level of transition amplitudes, and one can simply obtain the transition amplitude for one process by simply applying minimal substitution to that of the other. This is the sense of the crossing symmetry. So let's consider in general these 6 electromagnetic processes: Compton scattering, pair annihilation, molar scattering, Baba scattering, Bremsstrahlung, pair creation. You can pair them in this way. So the Compton scattering is, let's say, connected through crossing symmetry with the pair annihilation, the molar scattering with the Baba scattering, the Bremsstrahlung with the pair creation. And this you can also visualize in this last slide. Okay, so let's consider the molar scattering. Let's start from here. The molar, as we learn, we have to take into account 2 different interfering diagrams at first order. Okay, And it is the expression of the squared matrix element normalized to 2e to the fourth in terms of the Mandelstam variables. Okay. Now what do? You make a simple change. You interchange S by U in this expression, and you would obtain this other expression, which is the squared matrix element for the Baba scattering. Okay. So you see how the two are so easily connected by a simple S to U exchange in the matrix element. Another example is this one here. So you have the electron-muon scattering. Okay. This turns out to be the matrix element. In this case, we have only one diagram contributing because the final state particles are not identical. We have a muon and an electron, so we don't have an interference term. But then when you again change S with T, you obtain this other matrix element, which is the matrix element of the E plus minus into mu plus mu minus. Okay. So this is a powerful tool of QED, the crossing symmetry. So if you are able to calculate properly a diagram, either using first principle or using the QED, the Feynman rules, then with minimal changes, you can easily calculate those that are linked through the crossing symmetry. Ok? Allora, questa era l'ultima slide di oggi. Ci sono domande, dubbi? Tutto chiaro?
Sì, sì.
Bisogna meditarci sopra, ma sì.
Sì, chiaramente. Tutto ciò deve essere digerito con calma, ovviamente. Va bene. Quindi ora noi continuiamo domani, ci vediamo alle 11 e completeremo il capitolo della QED. Okay? Andremo a studiare adesso i contributi ad ordini superiori, come si comporta la costante di coupling della relazione elettromagnetica, come varia con l'energia, e poi studieremo una cosa molto complicata ma anche molto interessante, che è la rinormalizzazione della QED. Va bene. Sono le 11, ci vediamo domani.
Arrivederci.
Bene. Buona giornata.
Arrivederci.
Interrompo adesso la registrazione.
Arrivederci.
Arrivederci.